Going to make a start today, gents, on AC analysis and look initially at basic components when connected in AC circuits as opposed to DC ones. Starting with the resistor. So we're talking about a circuit with an AC source, current flowing. I'm using lowercase I to represent the fact that we would need to talk about an instantaneous value that is changing, positive end, negative end of that source. If I was to draw the phasors over time t, we'd get a voltage phasor like so, and the current phasor that are in phase with each other. We could draw what's called a phasor diagram where we had the voltage, I'm going to call that E in the circuit, the current I, is in phase. It should be in line with each other, but I've just drawn it slightly out so you can actually see it. There's no angle between them. In AC circuits, we change from resistance to impedance. Z in ohms for the overall opposition to current flow. So we can have an impedance phasor like so. So the angle of 0 degrees can be represented by R ohms angle 0 degrees, polar form, or R plus 0J ohms in rectangular form. I'm going to be recapping complex number arithmetic of both forms this morning because we need to use it. Okay, so that's per resistance. I'm going to put it back down in a minute. Current and voltage in phase with each other. Okay, in AC circuits, we call the overall opposition to current impedance instead of resistance, still measured in ohms. And the impedance phasor for a per resistor is one without an angle, so it's R ohms angle 0 degrees, or in rectangular form, R plus 0J ohms. Everyone reasonably happy with that? Yeah? Per inductance. Similar situation circuit-wise. We've got an inductor L, current flow in I, applied voltage E. Have I raced away from it? So here, what we've got, if we keep the voltage as the in-phase component in green, so there's our voltage phasor. With a per inductor, we end up with a current that is, if this is 90 degrees, 180 degrees, 70 degrees. So we can also, but we're also talking about time as well. We end up with a current phasor like so, that is 90 degrees out of phase with the voltage. Degrees out of phase. Would you say that current is leading or lagging the voltage? Lagging, yes. After. It peaks after the voltage does in time. Okay? We can draw an impedance phasor where that represents 0 degrees and the impedance phasor degrees positive. Call that ZL, okay? The impedance of the inductor, okay? We can also say it's equal to, that is equal to XL, inductive reactance. Talk a bit more about that in a minute. Okay, what we have here over here is the phasor diagram for current and voltage has E, the voltage, at 0 degrees, and then we specify the current I lagging by 90 degrees. Write that in there. Or equally pi over 2 radians if we had done our angles in radians. we can say that ZL, the impedance of the inductor, is equal to XL, and XL is equal to 2 pi FL. That's also equal to omega. Draw that a little less like a W. Omega L, because we know that omega and 2 pi F are equal to each other, and all of those measured in ohms. We can write ZL equals XL ohms angle minus 90 degrees. Polar form, ZL equals 0 plus 90 degrees. The impedance of an inductor, 0, comma, XL J, 0 plus XL J ohms. Rectangular form. Yeah, sorry, 0. Okay, so two ways of representing the impedance of the inductor is XL ohms at angle plus 90 degrees, or in polar form, or 0 plus XLJ ohms in rectangular form. Alright, everybody okay with that one? Yeah. Can I move on? Yeah. Right. By the way, I don't think I said it, but it's not possible, of course, to have inductance in a circuit because the coil has always got some resistance. It's also not possible, really, to have a circuit that is absolutely pure capacitance. So we're considering this in theory. So we've got a circuit here with some capacitance, an AC circuit, voltage, and a current I. Okay. In this circuit, if we draw the phasors for time t, similar angles. Again, for a series circuit, we'll keep the voltage as the in-phase component at 0 degrees, and our current this time would lead by 90 degrees. Yeah, because it peaks ahead of, in time, the voltage. Phasor diagram. E on the horizontal, 0 degrees. I 90 degree upwards. We could equally say that in a capacitive circuit, the voltage lags the current. And in an inductive circuit, we say voltage leads the current, and we'd still be right. Okay? But it's general to fix one phasor as the 0, 1, and in series circuits it makes sense, in parallel circuits it makes sense to do the voltage because every component is getting about the same voltage. Okay? So, impedance phasor. If that's representing 0 degrees, we have ZC, which is equal to XC, and that's 90 degrees downwards. I want to just add something to this slide as well. I want to bring, just out of that to the previous slide, the ZL represents the impedance of the inductor. XL represents the inductive reactance, which the impedance is equal to. F in the 2 pi FL bit is frequency in hertz. L is the inductance in henries. And omega is the angular frequency in radians per second. So that's just what all those terms mean. Right? Everyone got that? So in terms of this one, ZC is equal to XC is equal to 1 over 2 pi FC, or it's equal to 1 over omega C. I'm just going to I won't worry about putting omega on this one because that's the same thing. So ZC could be used to represent the impedance of the capacitor. It's also equal to XC, the capacitive reactance in ohms. F is the frequency in hertz in a 1 over 2 pi FC. And C is the capacitance in farads in both cases. Okay. So we can represent ZC as XL ohms angle minus 90 degrees, XC polar form, zero minus XCJ ohms rectangular form. Okay, everyone happy with that? So that are 3 different types of components that we're going to focus on in terms of carrying out IC analysis. Yeah? Right, everyone got everything down? Right, so we'll look at analysing a series RL circuit. When a voltage is specified for a circuit, if no angle is given, you assume 0. For anything not given an angle, you assume it's 0 degrees. So voltage is E, 24 angle 0. We'll have a 10 ohm resistor, and so R is equal to that. XL equals 8 ohms, angle 90 degrees. Again, you might only be given the ohmic value. If that's an inductor, you need to remember that the angle for an inductor is plus 90 degrees. Yep. Okay. Yeah. So if we look at Phasor diagram here, we've got yeah, and over here the impedance phasor. Can I go down now? Down or not? Yeah. Right. What we've got impedance-wise is we've got R equals 10 ohms. And we've got XL equals 8 ohms. And Z is the result of those at some angle theta in there. Yep. ZL is equal to XL. I'll put it in XL form now. So that's the inductive reactance. You've been given, in this question, you've been given that as an ohmic value, and I've added the angle on. If you were just given 8 ohms, you need to use the knowledge that that's 8 ohms, because it's an inductor, it's got an angle of 90 degrees. Okay? So that's the impedance situation, okay? So we can say, how can we represent this impedance here? The total impedance of that circuit. Yeah, we could do Pythagoras, but is there an easier way? That would help us get the angle. But rather than do all that separate, is there an easier way you could do it? You could go Pythagoras theorem. I'll tell you what. Let's do that down one side of the board. So we can say ZT, is equal to the square root of R squared plus XL squared. That's root of 10 squared plus 8 squared equals 12.8 ohms. How would you do the angle? Given the information you've been given. Yeah, you could use sine. What are you doing if you use sine here? You're using that value that you calculated and possibly rounded. If you're going to be using the opposite side, 8 ohms, and the adjacent side, 10 ohms. So what trig ratio uses opposite and adjacent? Yeah. So we can go tan of the angle is equal to 8/10. Therefore, the angle is equal to tan to the -1 of 8/10. Well, my answer's in degrees, so I'll have it in degrees, please. 38.7. Okay. Yep. Yeah. If the question has degrees in it, or it's asking for degrees or radians, then you need to stick with it. Also remember, if you've got a question involving omega, your angles are automatically in radians, because that's the frequency in radians per second. All right. So how else could we do that? How else have I, on the other pages, expressed the values of R, XL, and XC? Is there another expression we can come up with for ZT in this case? It has to be equal to, does it not? R plus XL. Because there's two impedances connected in series. Yeah. So how can I write those values differently? Right now? Yeah. How do I add these two numbers together? Adding rectangular numbers? No. Addition of what? Add the real parts. R plus nothing is R. Add the imaginary parts. Nothing plus XC is plus XC, XL, sorry, J. So we can write that number as a rectangular complex number in the form of R plus XLJ. Yeah. So now we can put the numbers in. 10 plus 8J and convert. So use the calculator to convert the polar form. So haven't got that in haven't got this number in rectangular form, we can then just use the calculator to convert to polar form. Okay. Lastly, and that's handy we got that in polar form, current I is equal to E over ZT in this case. 24 volts. Angle 0 degrees over is 12.8 angle 38.7 degrees. How do we do that polar division? Anyone remember? Subtract what? No, it's not. Yeah, you divide the denominator magnitude from the numerator magnitude, so you do 24 over 12.8, and the angle is 0 minus 38.7. You subtract the angle of the denominator from the numerator. So I've written that out in full there, and then we do that division, and what answer do we end up with? So we end up with a current of 1.88 amps with an angle of minus 38.7 degrees. So if we go back up here to this space that I left, we got a voltage E IR, so the current in the resistor be in phase with the voltage. IL 90 degrees out of phase, yeah, which gives us IT there at an angle of minus 38.7. And is that what we said happens with current in an inductive circuit, that it lags voltage? Okay. Can anyone remember the way in science I show you how to check whether you got that right? Whether current should be leading or lagging, voltage should be leading or lagging? Remember the word that we used? Civil. Yeah. I'll put that on a separate page. In the inductive circuit represented by L, current, looking at that half of the word, current is after voltage, therefore we say current lags voltage. Looking at this half of the word, okay, in either case we could equally say in a capacitive circuit voltage lags the current, and in a inductive circuit we could equally say that voltage leads the current, and we'd still be saying it correctly. Okay, but when you're doing the kind of calculations we've just done and you calculated the current, a check to make sure you haven't got any of your angles wrong in your arithmetic is to see whether it conforms to what we expect from the word civil about that circuit. You have to be a little bit careful when you've got a circuit that's got both capacitor and an inductor in it, because that circuit could at that moment in time either be overall capacitive or inductive in nature, depending on which components got the biggest part of the overall impedance. Okay, and we'll a bit more about that in a little while. Okay, so that's one way to check whether you've got your current angle correctly, or whether all your everything ties up, is to check it with the word civil. All right. So, RC circuit. That's AC. That's R. That's an R. Sorry, Elliot. That's because that board weren't writing properly when I done that bit. RC circuit. Resistor, capacitor. Okay? Again, if you're only given an ohmic value for the capacitor, you need to remember that it's a negative angle of 90 degrees for a capacitor. Impedance phasor. We've got R equal to 10 ohms. XC, 6 ohms. And a resultant phasor, ZT, in there at an angle like so. Again, we could use the two different methods. Magnitude can be calculated from square root of 10 squared plus 6 squared. And the angle is 10 to the minus 1 of 6 over 10. Ten minus 6, J. You've got to put the, after you put the comma in, you must put minus 6. Done that out for the video. So, using the two different methods, on the left-hand side here we used Pythagoras' theorem to find the magnitude of the overall impedance, and then use the tangent ratio to find the phase angle. Write that there. Okay. Over here, using complex numbers, ZT is the R minus XCJ, because XC is a negative value. That complex number, convert it in the calculator, we've got a difference. We've got minus 31 degrees. From using the word civil, we know that this answer's right. So where have we gone wrong here? What change would give us a negative angle there? Yeah, we need to put -6 there. We need to recognise, in this particular case, we're interested in the full polar form, and therefore we must show that that's actually a value of -6 ohms, because that's 90 degrees downwards. Yeah? So if you do that, and do that tangent again, you'll find that that angle comes out at -31 degrees, and then that'll be correct in there. So if you are going to use that method, you need to be careful. But then again, you need to be careful with the complex numbers, that you get the sign of the reactive part correct, according to whether that's XL or XC. Yeah? So in here, we've now got a phasor diagram where voltage E is there, IR would be in phase, IC would be 90 degrees downwards. Oh, hang on, no, whoa. IC is upwards. Just calculate our current. Do we get it right? Current I in this circuit is E over ZT. It's 24. Use the same voltage as before. Angle 0 divided by 11.7. Angle -31 equals 2.05 amps, angle 31 degrees. Yeah. So checking with civil, capacitive circuit, current's got a positive angle that's leading. So therefore, start that again. We want E there, IC in phase, IR in phase, so for me this morning. IC at 90 degrees upwards, IT in there at that angle, 31 degrees. Yeah. Okay, everyone happy with that? Yeah, good. It's all kind of revision anyway, because we would have done this in science, but did you want me to go back? RLC series. keep our same component values. What's an overall expression for ZT in terms of the Zs of each of those components individually? Forget about the values for a minute. Well, it is, what I want to do is express it as the impedance of the resistor plus the impedance of the inductor plus the impedance of the capacitor. Yeah? And we can write this as R. We can write that as XLJ. Yeah, we can write this as minus XCJ. Yeah. And what we can actually do is have an overall formula for the total impedance, that is R plus XL minus XC J. Combine those two terms in a pair of brackets. So the difference, the overall impedance is the resistance plus the difference between the inductive and capacitive reactances. So it will show you that if XL is that should show that if XL is bigger than XC, overall you'll have a positive reactive component. Circuit will be inductive overall. If XC is bigger, then there'll be a capacitive circuit overall, because that bit in brackets will come out as negative. Yeah? I can do. So that bit means all right? Yeah? Impedance phasor, in terms of this circuit, we'd have R equals 10 ohms horizontal. We got XC equals minus 6J ohms going downwards at 90 degrees. And we got XL equals 8J ohms, 90 degrees upwards. Then what we've got in here is a value that is XL minus XC J, the difference between those two, which is going to be, need to be a bit careful here calling that minus 6, because if you take away minus 6 you're going to add it on. The magnitude of that is 6. The difference between those two is 2 ohms. Our resultant phasor is the combination of all three sitting in there at an angle like so. Yep. And it should be remembered that the quantities XL and XC are frequency dependent, and therefore if we change frequency, those values are going to change, the phase angle is going to change, and the length of the blue line is going to change, and it could end up going down below the resistance and the circuit becoming overall capacitive through change of frequency, because the fact that XL is equal to 2 pi FL and XC is equal to 1 over 2 pi FC. When one goes up with frequency, the other will go down and vice versa. We talked about that a little bit when we talked the theory of your filters and things. Okay, so this circuit would end up with we've got a positive angle for the impedance, so with the angle for the current likely to be negative because of that, and therefore negative angle for current says we got an inductive circuit overall. Yep. And that would happen because XL is bigger than XC. So if we do that maths now, ZT is equal to R, 10 plus 8 minus 6 J ohms. Right, that's often going to need it in polar form as well. We might, in some questions, need it again in that form. So convert to polar form. There's E over ZT. That was 24 volts. Angle 0 over 10.2. Angle 11.3 equals. If an angle's not stated, then you assume 0 degrees. Yeah. 2 point something amps. .35 amps. Angle minus 11.3 degrees. And does that ring true for an inductive circuit using the word civil? Little check. CIVIL, inductive circuit, current lags voltage. Yes, we've got our angles right. Okay. So that's kind of a bit of a recap in a way of some stuff that we will have done before in science anyway, and talked a little bit about up front here when we want to see how the filters worked. So that's how we can analyse a simple series circuit where we might have both inductance, resistance, inductance and capacitance. Okay, all right with that? Yeah?